Hey astronomy, it's Miss Ruark. We're in podcast 6.2, chapter 6. We're talking about telescopes. So we just talked about light and how light is a particle and it's a wave, and we talked about the spectrum of light, not just the visible light, but also all of the other radiation that comes along with the electromagnetic spectrum. So now we're going to talk about telescopes because telescopes need light. All right, so telescopes, there are two types of optical telescopes that you can have. You can have a reflecting telescope or a refracting telescope. Okay, the difference between the two is a reflecting telescope will use mirrors to capture light, where the refracting telescope uses lenses. Okay, reflection, think reflection, reflecting, you have to have a mirror or something that can reflect that light, so mirrors. Okay, reflecting telescopes have a primary mirror, which would be the main mirror that accepts that light, and then the refracting telescope would have a primary lens or a main lens which accepts that and captures the light. Okay, the reflecting telescopes are going to be much less expensive, and the refracting telescopes are going to be extremely expensive because of the equipment that goes into making them. Okay, so an example of these two would be here. You have the reflecting telescope has a mirror, which would be this mirror here. And this mirror is shaped so that when the light comes in, it can bounce off and be seen here. Now, it's bounced off upside down. Okay, so when it comes through, it's bounced off upside down. So anything that you're looking at through the telescope is going to be opposite of what it actually is. So if you're looking at an object and it seems to be going off to the right, it's actually going off to the left. Right, because it's the opposite. It's inverse. All right, with a refracting telescope, there's a big lens, which is made out of glass, and there's this big lens here, and it captures the light, and it inverses the light, and it turns it upside down. All right. So a refracting telescope might be nice. They are nice, but there are some disadvantages to these. Okay, you have chromatic aberration, which means that the different wavelengths of light will be focused at different focal lengths. Okay, so that means that once the light comes through here, it gets separated into, because this is like your prism, okay, it's going to be separated into the colors of light. And some of these colors, because they have lower wavelengths, will focus at a shorter distance than will the other ones. Okay, so you have chromatic aberration, and a way that this can be corrected is if you put a second lens of a different type of material in there. However, it's not completely eliminated. Okay, here's the second lens right here. Okay, another problem is that they are difficult and expensive to produce, and the reason for that is because every single surface that you have in a refracting telescope has to be perfectly shaped, especially that lens. The glass that's used for the lens has to be flawless. If it has any flaws on it whatsoever, it's not going to correctly capture the light and send the light out. Okay, and the lens can only be supported on the edges here, so you can't actually have anything back here to support the lens. And these lenses made out of glass, they can get pretty heavy sometimes. All right, so 3 powers of the telescope. The telescope is good for 3 things. The first thing that it does is it makes images brighter. So things that are faint, you can actually see through the telescope. A nice thing, if you're out looking on a sky or on a night when the sky is clear and you look, you see with your eye and you see a star. Well, then you go look through the telescope at that star, and not only do you see that star and it's way brighter, but you also see all these little faint stars that you didn't see before. Okay, so it makes things brighter, and it does that with a light gathering power, LGP, which is the ability to collect that light. And the light gathering power is going to be proportional to the area of the objective. Now, in this case, an objective is a lens or a mirror, whatever's collecting that light. All right, so let's say that we have a 24 centimeter lens and we have a 4 centimeter lens. Okay, well, the ratio between those two is a 24 to 4, and if we simplify that, that would be a 6 to 1 ratio. Okay, so we could say that the 24 centimeter lens is 6 times, captures 6 times more light, correct? No. That's wrong. The reason for that is because it's proportional. Okay, so if it's 6 times, if there's a difference of 6 to 1 here, then we have to square that. So then it would be 36 times more light that the 24 centimeter lens will capture than the 4 centimeter lens. Okay, so bigger is better in this case. All right. They can give you more detailed images, and the reason they do that is because they have resolving power, or the ability to reveal finer detail. Okay, now with a telescope, you can't completely and totally take away all of the fuzzies, if you want to say that. Okay, and the reason for that is because each telescope has a diffraction fringe. Okay, and the diffraction fringe is the fuzziness of the image, or the amount of fuzziness that's going to be able to take away. Yes, fuzziness is a technical term. No, actually it's just Miss Ruark's term. But a diffraction fringe is taking the fuzziness away from that image and making it more detailed. Right? And the larger the telescope you have, the larger the telescope you have, the smaller the fringe, or the better resolving power you have. So you want a smaller fringe to have a better resolving power. And resolving power is going to be worse for the longer wavelengths because they have less energy. And you have to remember that you can have something that has great resolving power, but if the lens isn't high quality and the atmospheric conditions are bad, then the detail will be bad as well. All right, so this is what I mean by resolving. Here's a picture of something that you would look at that normally looks like one big thing, but you can tell now because it has been resolved, that there are actually two stars there instead of just one. Okay. Also, another thing that we need to talk about is seeing. Okay, and when we're talking about seeing, it's talking about the clarity of what you're being able to look through. Okay, so the seeing of the atmosphere here is very poor, whereas the seeing on this side is very good because you can see it's not as fuzzy. All right, the third thing that it helps us with is it makes larger images, and it has a magnifying power, which is the ability to make the image bigger. Well, the magnification, way you figure that out is you take the focal length of the objective, which would be the lens or the mirror, and you divide that by the focal length of the eyepiece, and that gives you the magnification. High magnification doesn't mean there's going to be more detail, it just means that it can give more detail, but you also have to think about the resolving power, the lens quality, and the atmosphere. All right, another thing that you need to remember, and I don't know, here it is. The smaller lens number tells you that it's a greater magnification. So if you start off with a 20, a 10, a 5, of those three, you always want to start with the bigger one, which is a lower magnification. So you start with the 20, find your object, then switch to the 10, which is going to be greater magnification, find your object, then go to the 5, which is going to be even greater magnification, and you should be able to see some good stuff. All right, when we talk about telescopes, we talk about them in terms of diameter, not magnification. And the reason we do that is because both the, let's come back here. Sorry. Both the images, the brightness of the image and the detail of the images refer to or depend on the diameter of the telescope and not the magnification. Okay, light pollution is something that's going to restrict your views, and light pollution is given off from any nighttime lights, so outside street lamps, or the ads and the lights from all the businesses, that would be light pollution. Okay, now the moon is a natural form of light pollution, and that gives us great night pollution. It can help us by giving us a little bit of something to see when it's not full. But when it's full, it makes it hard to see everything we want to see. Okay, so the best conditions for observing things are going to be on high altitudes, which are really tall mountains above the clouds, and in a dry atmosphere, so that you don't have a lot of stuff to, a lot of gas and things in the air to go around. All right, newer telescopes, nowadays they are made with lightweight mountings, thin lightweight mirrors, and they use a computer to reduce the distortion of the atmosphere. Okay, the older telescopes were very heavy, they didn't have the computers, the mirrors and the lenses were extremely heavy, it was just horrible. All right, so examples of the newer ones are the Gemini telescopes. It has an 8.1 meter, it should say mirror, not mirrors. And there are two of them located, one in Hawaii and one in Chile. And they are there so that they can cover the total expanse of the sky, north and south hemisphere. And we also have the Very Large Telescope, the VLT, that's exactly its name. It's located in the Andes Mountains of northern Chile. It is actually 4 telescopes. There's one here, one here, one here, and one here. 4 telescopes, And they have computer-controlled mirrors, and the mirrors are 8.2 meters long or in diameter, and they're only 17.5 centimeters thick. Now, the nice thing about this is they can all work independently as 4 telescopes, or they can all be combined together to work as one big telescope. All right, so let's talk about adding them all together. Interferometry. Okay, interferometry is when you connect multiple telescopes together to work as one single telescope. And when you do that, it gives an extremely high resolution, so the resolving power is good. Okay, so the VLT, which you just saw in the previous picture, these can all be linked together by tunnels in this mountain. Okay, and there's actually 2 or 3 other telescopes in there that link them all together as well. And when they link together, they work as one big telescope that has a 200-meter resolution. So it's as if we went from an 8-meter telescope to a 200-meter telescope. That's huge. That's huge. All right. Special instruments. So when you look through the telescopes, you see stars that look like points of light, planets that look like little disks, and galaxies that look like hazy patches. We can add special instruments to analyze the light that comes through the telescope. Now, they used to have different ones, but the nice thing is they changed it all because of the use of technology that we now have charge coupled devices, or CCDs, and they act as that one that integrates multiple instruments to be put onto the telescope. So a CCD is a specialized computer chip that has 1 million light detectors, and they're all arranged around the size of a postage stamp. So think about that. That's a lot of lights in a little size. Right? They can detect both bright and faint objects in a single exposure, and they can store the pictures in the chip as numbers. And that makes it easy for whoever's using it to manipulate the picture and bring out details that you would otherwise not be able to see. Okay, so how can they manipulate them? Well, they can show the astronomical images as negatives or false color images. So as a negative, what would normally be dark is going to be bright, and what would normally be bright would be dark. Okay, so here's is a picture of the sky with stars. This is a star cluster here. Okay, and here it's been blown up. You'll see that all of the white is actually dark space, and all of the dark spots here are actually stars, and it allows you to see the detail a little bit more. Okay, we also have right here is a false color image, and a false color. In a false color image, they take and manipulate the color of it so that you can see more detail. So this here is a picture of a solar flare, and normally you would see when it's a solar flare, this would be the sun. It would be nice and orange, and then the flare part here would be a darker color. And that's not the case here. They wanted you to see the flare, not the actual sun. So they change and make it a false color. Okay, another example of a false color would be this picture of the moon. Okay, normally you see the moon and it's all white or gray. Okay, but this gives you a chance to see in more detail the craters and the volcanoes, we call them volcanoes, on the moon. Okay, and then one more for you to see, and this would be a picture of a spiral galaxy, actually 2 spiral galaxies here. Okay, but it's a false color image so that you can actually see all of the stars and all of the items that are involved in this spiral galaxy and on all the other little things next to it. Normally you wouldn't see all of these dots here. These would be your stars, but you wouldn't see them because the detail isn't there. Okay, another thing that can be added to the telescope is a spectrograph, and the spectrograph is used to analyze light in detail. And what it does is acts like a prism. It takes the light, the white light that comes in, or whatever color is coming in, and it breaks it up and spreads it out according to the wavelength, and it forms a spectrum. Okay, now your spectrum of color goes from red to purple, Roy-G Biv, right, or Roy-G Biv. All right, so the spectrum, if you were to look at a spectrograph, it would probably show up where it's showing you just the color of wavelengths that are coming in, or it could be a continuous color like this one, and it would be blacked out where the color is not coming in. All right, and I think that's it. So I'll see you in class.